Hello everyone, welcome to today's lesson. We are looking at circular motion today, or motion in a circle. So motion in a circle, just stop it there. Motion in a circle. Okay, motion in a circle. So under motion in a circle, we are going to discuss a number of concepts or terms with reference or in comparison to motion on a straight path or in a straight path. So motion in a circle, if you go to the tutorial sheets that we are having, is tutorial sheet number 6. So motion in a circle, which is tutorial number 6. That's the tutorial sheet that we are doing. So we've got a number of questions, about 10, but we are going to start with talking about a few concepts before we go into discussing the tutorial questions, or before we solve any of the questions. So rotational motion is important, or circular motion per se is very important in physics and in our daily activities, because if there is no motion in circles or rotational motion, we would not have it's not going to be possible for cars to move. Mind you, wheels move in circular paths, or they rotate, and by so doing it causes circular motion or rotational motion, and those wheels, as they are rotating, they cause the car to move. If you look at another example, that we can look at is an example of the earth. The earth rotates. Because of the fact that the earth rotates, we are able to have days and nights due to the rotation of the earth. So it's important for us to understand the concepts of rotation and what it brings about. So we've got some terms in rotational motion or motion in a circle. Terms such as angular speed. Okay. Terms such as angular speed, angular acceleration. We can talk of other terms. We'll talk about other terms as we go on. But from linear motion, we had talked about displacement or change in position. If we're talking about it in the x-axis, what we were calling it change in x. If it was with reference to the y-axis, it was change in y, and so forth. So that can be an object moving from point A to B. So the distance, the separation distance, is what we are calling as the displacement in a specific direction. Then, after talking about displacement, we talked about the change of displacement with reference to time, and that's what we called velocity, where velocity or change in velocity was the change in displacement with reference to time, which was like x final. If we are talking about motion in the x-axis, minus x initial divided by the time final minus the time initial. Meaning, if at all we start from a specific point, which is at A, and if we take A as 0 and we move to a specific point B and we take B as, let's say, 20 meters, meaning that the change in distance or displacement will be the final time when we stop and the initial, or minus the initial time when we start this motion, which will be 0. So we'll have 20 minus 0, and that will give us 20 meters per se. And then how much time did it take for this journey to complete? So if this journey took 20 seconds, the time the journey started, the timer was obviously at 0, and the time when it stops, it will have a specific time. Let's say maybe 5 seconds, maybe 20 seconds. That will be your final time, and then you can do the subtraction, and you'll be able to get the velocity. After talking about velocity, we also talked about acceleration, which was the rate of change of velocity with reference to time, meaning that acceleration was equal to change in velocity divided by the change in time, which is equal to the final velocity minus the initial velocity divided by the time, which is t final, t initial. Here we are going to get the acceleration. So this is with reference to linear motion. But when we talk about rotation in a circle, there are some different terms that we use. Let's take, for instance, if you have a circle per se, and you have a car that has moved from a point in a circle, let's say this is point B. If it goes round the circle and comes back to point B, and you want to find out how much distance did this car cover, or did this object cover when it moved from point A and back to point A in a circular path, how much distance did it cover? If you use mathematics, you'll find that the distance covered is simply the circumference of the circle. And that circumference of the circle is given by 2 pi r. 2 pi is the total angular space that has been covered, whilst r is the radius of this circle, the circular path that has been covered. So you've got 2 pi r as the circumference. But what if I just want to find, let's say, the radius or the angle? I've been given the circumference and I've been given r, assuming maybe this car did not move from point A and back to point A. Maybe it moved from point A and went to point B. And you want to find out how much space was covered, the distance, because this is a circular path. So if it moved from point A to B and you want to find out how much of this space it has covered, you will need to know the angle that has been subtended, the angle here, which is theta. You have to know theta so that you'll be able to find this distance, because for you to find the circumference, you need the angle. In this case, we have 2 pi. 2 pi is the angle, the angular distance, or the angle, the total angle of any circle. We know that a complete rotation of a circle has got 360 degrees. That is in degrees, we've got 360. But then if we talk about another unit which is known as the radian, the radian has got 2 pi in terms of angles. So we have 360 degrees being equal to 2 pi radians. So the fact that this 2 pi radians is the angle in radians, meaning it is the angle for the whole circle. But what if I only want a portion of this? How do I get this angle? Okay, so we can say the circumference of the circle is equal to the angular distance, which is in radians, of course, it's 2 pi, multiplied by r. But then what if I have not been given the angle? I can say that it is simply theta, isn't it? I can call it theta and then multiply it by r. Okay, now this C here is the circumference, or the distance that has been covered. And distance can be represented by another letter, which is S. We can represent it as S. So we can say that S is equal to r theta. I've not changed anything here. I have simply just gotten the theta and I've put it in front of the radius. So that's what I have here. In case I want to calculate the distance that this object has moved from point A to point B, I can simply use this formula. In a case that I'm missing any one of them, let's take, for instance, I've been given the the distance that it has covered from point A to B, and I also have the radius of this circle, but then I do not have the angle. How do I go about it? It's easy. You simply make theta the subject of the formula, and you have S divided by the radius. Okay, where theta is your angle, so we can say where theta is in radians. Okay, so the full term is radians, but we use RAD, which is rad, just to simplify that. So that's what we have here. We need to find the angle in radians. In case we've not been given the angle in radians, but we've been given the angle in degrees, then we have to figure out how we are going to move from one unit to the other. So, from what I'm just from explaining, the angle 360 degrees is equivalent to 2 pi radians. All right. Now, if 360 degrees is equals to 2 pi radians, meaning we can convert from one unit to the other. Let's take, for instance, I want to convert from degrees to radians. How do I go about it? Or if I want to convert the angles from radians to degrees, how will I go about it? So you have to look at the conversion factors. At this stage, I believe everyone has learned how to make conversion factors. If not, let's look at angles. So we look at theta in degrees is going to be equal to, if we are converting from degrees to radians, we'll have theta in degrees multiplied by 2 pi radians divided by 360 degrees. The reason why I've divided by 360 degrees is because 360 degrees make 2 pi. So this way, I'm going to divide the degrees, will go, and then I'll remain with the theta values, the value that we had in degrees multiplied by 2 pi radians divided by 360. Mind you, the degrees have gone, meaning that the value that I will get after the calculations will be in radians. So let's assume that the angle was 45 degrees. If we have 45 degrees and we want to convert it to radians, we are simply going to multiply, we are going to multiply it by 2 pi radians divided by 360. So if you multiply that, I have a calculator. So if you multiply that, you'll find that you have 45 by 2 pi, which is going to give you 282.7 divided by 360. It will give us 0.7. So our angle will now be, so theta will be equal to 0.785 radians. So we have converted 45 degrees is equivalent to 0.785 radians. But then what if we want to convert from radians to degrees? So if we've got an angle theta in radians and you want to convert it to degrees, you are simply going to have to multiply your angle theta in radians multiplied by 360 degrees divide by 2 pi radians. So if you take note, here on top, I multiplied by 2 pi radians divided by 360 degrees. The initial value here was I had the value in degrees and I wanted it to be in radians. So meaning, because I want to have the value in radians, I have to put the radians on top and the one that I want to get rid of at the bottom. This is just for simplicity, the concept that I've been using for a while. I simply look at what I want to end up with at the end of the day. If I want to end up with radians, I'll put the radians on top. And if I want to get rid of the degrees, I'll put them at the bottom, so that if I divide through, the degrees will divide with the other degrees and I'll only remain with the radians. So in the same way, we can look at converting from radians to degrees. I want to end up with degrees at the end of the day and I want to get rid of the radians. So the radians, if I put it at the bottom, it is going to divide with the other radian and I'll remain with my value in degrees. So meaning that the value that I'll get in degrees will be this, the radian will divide through with the radian, and it will be the angle in radians multiplied by 360 degrees. And whatever value you are going to have, you simply multiply it by, divide by 2 pi. So whatever value you are going to have in radians, you simply multiply it by 360 degrees and divide it by 2 pi, and you're going to get the value in degrees, because those are the units we've remained with. But there's also another unit which we call the revolution. In most cases, when we talk of revolutions, we are talking about something that has moved from its original position back to the same position. In short, we are talking about oscillations, circles. All right, revolutions can be considered as circles. If a body starts moving from point A, it goes around the circle and it comes back to point A, meaning that this body has rotated one complete circle. Hence, it has made a complete revolution or a complete oscillation. So, meaning, as the body is completing one revolution, it has covered 2 pi radians if we talk of radians, and it has also covered 360 degrees if we are going to talk about degrees. So we'll have one revolution. We'll have one revolution being equal to 2 pi radians, and then equal to 360 degrees. That's what we have. Meaning, if you want to convert between angles, let's take for instance, you have got an angle of, whatever value of angle you have, let's take it as theta. In degrees, theta in degrees, and you want to convert it to revolutions, you simply have to multiply it by, like I said, you look at what you want to end up with at the end of the day. I want to end up with revolutions, so I can change that to revolutions divide by, so one revolution is equivalent to 360 degrees here, so we divide by 360 degrees, so that the degrees will divide through, and then I'll remain with theta revolutions, right, divided by 360. So whatever value you are going to get, it will be in revolutions, because these are simply magnitudes. We do not have any other units apart from the revolution. So that's that if you want to convert. The same with radians. If at all I was going to convert an angle theta radians, and I want to convert it to radians, to revolutions, I will simply multiply it, one revolution divided by 2 pi radians. So the radians will divide through with the radians, and I'll have theta revolutions divided by 2 pi, right? So that way I have converted from degrees to revolutions and from radians to revolutions. That's how we go about converting between units. So if you are also, because of the fact that it was already covered for when you looked at Newton's laws, converting in terms of time between seconds and minutes and the like. Because as we'll be doing the tutorial sheet, you'll notice that some units will be in revolutions per minute, radians per minute. So you also have to take note of the fact that the SI units for time is seconds, and how many seconds make up a minute, how many minutes make up an hour, and the like. You need to make sure that you are familiar with that. All right. So now, having talked about this, we can look at motion in a second now, per se. Like I was saying, we have, see, okay. So if we draw an X or Y plane here, and we have a circle. Right, my drawing is not accurate, but we will have R here from what I'm explaining, and we have theta, and we have this distance here, which is subtended by that as S. So we said S is equal to R theta, which is the angle multiplied by that. And we can also say that theta is equal to S divided by R. So for a circle of radius R, 1 radian is the angle subtended by an arc length equal to R. So we've talked about converting between degrees and radians and revolutions. We've already discussed that. It's not a big deal. But you should also take note of the fact that because 360 degrees is equal to 2 pi, how about 90 degrees in radians? How much will it have? So in radians, we are going to have 90 degrees multiplied by 2 pi radians divided by 360 degrees. So we're going to end up with 90 degrees multiplied by 2 pi, which is equals to 565.48 divided by 360. This will give us 1.57, which is equals to 1.57 radians. Or we can say, if we write it in terms of pi, we can have, let's say, if we divide, if you look at 360 degrees, 360 degrees has got 90 degrees here. If you look at it, this is 90. The whole angle here is 90, 90, 90, meaning 360 is divided into 4 parts, where each part is equals to 90. And if 2 pi is equals to 360, so we can divide 2 pi divided by 4 to get the radians in terms of pi, and we are going to have pi over 2. So meaning that 90 degrees is equals to pi over 2, which is also equal to 1.57 radians. So we have that. You can prove that if you divide pi, divided by 2, if you divide pi by 2, you are going to get 1.57 radians, or 71 radians if you keep on rounding off like that. So we have that information. Now, if we talk about, if we go back to linear motion, where we discussed displacement, acceleration, velocity, and the like, we'll find that they can also be talked about in circular motion in similar ways. So if at all we are recording time, right? If we're keeping track of the time, we have a timer, and a body has moved, let's say from, like I was giving an example earlier, from point A to point B. if you start recording the time here, it's going to be T initial, okay? And if you record the time up to here, this will be our T final. So a body has moved from A to, okay, let's try to draw a different diagram just to enlarge this. Okay, we have an XY plane here. So assuming this is the circle at hand. And then we have an object which is starting from, let's say, this point. It's starting from here. Okay, this is point A. And then you keep a record at point A. It is subtended by this angle here. If we record this angle, we can call it theta initial, because at this point, this is its starting position. Then, if we are going to keep track of the time, this will be our T initial. If this body moves to another point somewhere here, we'll take this as our point B, meaning that this body has moved, or this particle, whatever you're looking at, has moved this much distance at B. And if you look at the timer when it stops moving, you are going to find that this will be the final time. Now, the angle that it would have subtended as it is moving would be up to here. So we can take this as our theta final, or our final angle. And then, because of the fact that it has moved within this distance, we can call this as our R. So this is of course the x-axis, and this is the y-axis. So when this body moves from theta initial to theta final, it has covered this much. Now, if we go back to the formula, S is equals to R theta, or theta is equals to S over R. This is what has happened, meaning in terms of distance, or in terms of angular distance, this body has moved a distance, or an angle, has covered an angle of theta final minus theta initial, because it started from here, point A, and went to point B. And then theta initial had this angle, was subtended at this angle, so here, and then the theta final went on up to the next angle. So we'll have that. Then in terms of time, how much time elapsed as that was happening? So we can look at the time as T final minus T initial. Since we have the time, is it possible that there is a relationship between these two, the change in the angles, or in theta with reference to time? Yes, there is, and that is what we call angular speed. All right, when we talk about an object moving from A to B, it is causing a form of displacement, because it is moving from one point to another. So, except the fact that it is no longer moving in a linear path, but in a circular path, so the term, instead of it just being displacement, the term is known as angular displacement. So angular displacement, which is the theta and is represented by theta final minus theta initial, just like we did in linear motion. X final minus x initial, that as our displacement. Now in an angular form, we're going to call it angular displacement. Time is the same, whether in linear motion or in angular motion, we're simply talking about a change in time. So what if we want to find out the speed, or the rate at which the angular displacement is changing? Now we talk about angular speed. Angular speed is represented by a Greek letter known as omega. So omega is equal to the change in angular displacement with reference to the change in time. which is going to be equal to theta final minus theta initial divided by t final minus t initial. So we have that as our angular speed. So we've got angular speed. Now, from angular speed, which is what we have here, we can also look at other terms. Okay, we'll discuss more on this as we are doing examples, but this is just to familiarize with you, to make you familiar with the term. Now, if we want to find out the speed or the rate at which the angular speed is changing, then we are going to talk about another term which is known as angular acceleration, right? That's angular acceleration. Or before we go to angular acceleration, we can also talk about average angular speed. So by angular average or average angular speed, we are talking about situations where we've got different speeds, just like we had in linear motion, where we had bodies moving at different speeds, and then we would find the average of that. We can also do the same with the angular motion. So with angular speed, we are talking about the average speed, which is simply more like what we are talking about here anyway. We'll see how many examples we are going to do with reference to this. Then we can talk of angular acceleration. So angular acceleration is simply the rate of change of angular speed. So we are going to have the change in speed or change in angular speed divided by the change in time, which is going to give us omega final minus omega initial divided by t final minus t initial. So that's what we have as our angular speed. Now, angular speed, as you have seen, is being represented by a Greek letter known as alpha. Yes, alpha. So when we talk about this, if you take note, it's similar. We've talked about theta as our angular displacement. So far we've talked about theta, which is angular displacement, and so we have theta, which is angular displacement. If we go back to linear motion, this is just like talking about x or y. So this is change in x, change in theta. We're talking about change in x, which is simply displacement, which is of course linear. Then we've also talked about change in omega, which is the angular speed. Now, speed, from the previous times we had talked about the rate of change of distance with reference to time, and then when we talked of it being a vector quantity, the term velocity was brought up. So here we have velocity, the change in velocity, which is simply velocity. It's like speed. Velocity is just speed in a specific direction. Then we'll have we also have acceleration, which is acceleration in linear terms, but in angular terms, we've got angular acceleration. So that's what we have. Now, when we talk about these being vectors, right? Like for instance, acceleration, we know that acceleration is a vector quantity, meaning it has got direction. In linear terms, we are talking mostly forward as positive and backwards as negative, with reference to however you are solving the question. Now, with angular motion, we take clockwise motion as negative and anti-clockwise motion as positive. What I mean is, if we start from here, a body starting from here, if it's going in this direction, then we are going to take all the motions in this direction as negative. Because if you look at angles, we know that when we are measuring degrees, we follow the counterclockwise direction. So meaning from here to the next point, this is counterclockwise, and that's how angles increase. So from here to here, we've got positive 90. Sorry, from here to here, we've got positive 90. All right, from here to here, we've got positive 180. Here to here, we have got 270 and then to 360. So if we start going in an opposite direction, then we are following the negative path. So when you're looking at angular motion, clockwise motion is considered as negative, whilst anti-clockwise motion is considered as positive. So counterclockwise or anti-clockwise is positive, whilst clockwise is considered as negative. So that's what we have for now. So now from these terms, we can even come up with terms such as force. We can look at from linear motion, we had force is equal to ma. All right, that was what we're using. Then in circular paths, we can also look at similar terms. If we look at force being equal to mass times acceleration and so on. So we'll discuss some more as we'll be doing examples. Okay, so now there's also other terms that you can look at. Terms like if you're talking of angular speed, there are also terms such as frequency. Frequency, from if you go back to high school, frequency was solved using the formula n divided by t, where n is the number of rotations and t is the time it takes to complete those rotations. Meaning that we are saying that frequency is simply the rate of change, or the rate at which an object is able to oscillate from one point to another. Okay, so the rate, in short. So frequency is usually measured in seconds inverse, which is also equal to a hertz. That's what we have frequency for. So if at all we want to find the frequency with reference to angular speed, we use the formula, okay? Angular speed is equal to 2 pi frequency. Now, the reason why we've said 2 pi frequency, if you look at 2 pi is the space that has been covered, all right? In terms of angles, we've covered that much angle. But then time, we go back to the angular speed formula where we've talked about the change in angular displacement divided by the change in time. So the change in angular displacement divided by time, relating it to frequency. Frequency is the number of rotations, right? How much it is rotating. Now, this can be considered in terms of angles. Okay, so you can say, you can talk of it being n as the number of angles or the number of degrees that you are working with, and then 2 pi is how much space was being used. Okay, the frequency, all right, just a second. Seems like it's a bit windy where I am right now. Okay, 2 pi frequency. So explaining how this is coming to be. So change in angular speed divided by time. Okay, so if I say theta omega is equal to, right, theta final minus theta initial, meaning this is how much it is moving about. But then how many rotations has it made? Okay, it can be n, and that n divided by t. Okay, so the n, meaning we've made how many rotations in terms of angles or revolutions, how many have we made? If we've made one, then it's simply going to be 1 multiplied by the angle here. If it's 2, we are going to have 2 and the like, but then it is divided by time. So meaning that we can say omega is equals to theta final minus theta initial multiplied by n over t, where n over t is the frequency. And theta final minus theta initial can be taken as 2 pi, or the value for the complete revolution, which is going to be equal to 2 pi frequency. So that's the relationship. In case we've been given frequency, we can calculate omega. In case we've been given omega, we can calculate the frequency with reference to that. So those are the terms. But then there's also the relationship between linear momentum. Sorry, I don't know why I keep talking about momentum. Right, there's a relationship between angular and tangential quantities. So relationship between angular and tangential quantities. So this relationship, from what we have on top, we've got S is equals to R theta. That's the relationship. Okay, this is a relationship because if you look at it, this is more of linear because we are moving from point A to point B. If, for instance, you have, let's take, for instance, an example of a tissue. You roll it, it's in a circular path. Okay, it's in a circular kind of, as you are unrolling a tissue, it's in circular way. But if you get it, you can simply straighten it and it will be linear. So meaning in terms of circumference, even this circle, it might be circular at this point, but we can cut it and then it can form, we can have a straight line or a straight wire if at all it was in form of a wire. And this distance here is simply equal to c, which is equals to 2 pi r. That's what we have. So meaning that, see, there's a relationship between the angular path and that. So here this can be turned into linear and it is related to the angle that is being subtended here. So we can say that there's a relationship between the angular value and the linear value. So S can be considered as the linear, whilst theta is considered as the angular. So the relationship that they have is this one. What about velocity? How is it related to angular speed? So velocity is also related to angular speed by the formula r multiplied by omega. Okay, then we also have the relationship between acceleration, which we are calling as tangential acceleration, which is also related by r omega. Oh, sorry, r alpha, since alpha is the symbol we are using for acceleration. So I want to explain much about tangential acceleration because I believe you did that in your lecture. So for now, we can just let it be like that. So that's what we have. But now, we can also look at another term, which is centripetal acceleration, before we talk about solving the questions. So let's look at, okay, centripetal acceleration. Okay, so centripetal acceleration, which is represented by AC, C for centripetal. So what exactly is centripetal acceleration? If you have, if you get a ball, right? If you get a ball here and you tie it to a string, okay, you tie it to a string at this point, so you have a ball there and you have a string, and then you start moving it or wiring it. Yes, if you start rotating this or wiring it, you would find that this ball will move in a circular path. It will move in a circular path. Okay, so we can talk about it being we have a ball here, okay, and then you've got the string, of course. So this ball, because it is being what, it's going to keep moving in a circular path, but then this ball can choose to go in this direction. Okay, it can go in this, it can choose to go in this direction, it can also go in this direction, but it keeps moving in this circular path. What causes it to move in that way? Okay, so centripetal acceleration, if you have, like I was saying, if you've got a ball, or you can take it that you're talking about a point mass. So a point mass M, which is moving with constant speed around a circle. So you've got this circle and it has a certain radius R. So if it is moving at a constant speed V, around a circle of radius r, then it undergoes acceleration, isn't it? Because acceleration is the change of velocity with reference to time. So the fact that a body is moving with constant velocity around a circle which has a radius r, means that it is undergoing this acceleration. So although the magnitude of this linear velocity is not changing, the direction of the velocity continually changes. So if it is here, the velocity is constant, meaning the initial velocity is the same as the final velocity. But if you look at it, when the ball is here, its direction, the chances of it going out of this circle are there, and it can also go into this path, but it keeps going like this. So meaning it goes like this. When it reaches this point, instead of it going in this path, it follows this path, right? So again here it will follow this path. Another point, this path. So meaning if you look at it, it's changing its speed, right? Keeps, sorry, not speed, its direction keeps changing. So because of the fact that this direction keeps changing, this change in velocity gives rise to an acceleration which is known as the centripetal acceleration of the mass. And this acceleration is directed towards the center, right? Because of the fact that it is directed towards the center, that's why it has a tendency to move in this path. It is trying to get to the center, but it keeps moving in this path. Keep trying to get to the center, and it keeps being pushed. Yeah, it's as it is moving around this circle, it is being forced to move towards the center, hence it curving, right? It keeps curving as it is moving because there's something at the center that is causing it to want to move. So there's an acceleration, which is a centripetal acceleration, that causes it to want to move towards the center. So this acceleration is what we call centripetal acceleration, and its magnitude is given by so centripetal acceleration has got a magnitude which is equal to the tangential speed. The reason why we are calling this speed as tangential is because this is a circle. When you have a circle, okay, when you have a circle, this is the tangent, right? So there's a speed that it is moving with around this circle, which is the angular speed, but then the tangent of this speed is the tangential speed, all right, which is also the v. So the tangential speed squared divided by the radius. So the radius of the circle or circular path, yeah, can take it as the radius of the circular path. So the tangential or the centripetal acceleration, the tangential speed I've said is linear. So meaning we are talking about it being v, and it is tangential speed squared. So this is going to be divided by r. Okay, but from the work that we're just doing here, the relationship between tangential speed and angular speed is this. Okay, so we can substitute in this so that we'll have r omega, which is now the angular speed, divided by r. So if we do that, we are going to have r squared omega squared divided by r. So there we have this. So the centripetal acceleration can be given by this r can divide with one of the r's there, and we'll have r omega squared. Okay, so that's what we have as the centripetal acceleration. Then as this ball is being moved, as it is moving around this circle, because of the fact that it has got an acceleration and it has a mass, meaning that we can come up with a term which is known as force. From linear motion, we say that force is equal to mass times acceleration, and this mass is being caused by an acceleration on the body. So because of the fact that the acceleration is centripetal, meaning that the force also is centripetal, because the force acts in the same direction as the acceleration. So meaning that with reference to centripetal force, to centripetal acceleration, we can talk of centripetal force. Now this centripetal force is MAC, where AC is the centripetal acceleration. So meaning we can say that the centripetal force is AC on top here is equals to r omega squared. So we can say this is equals to mr omega squared. That is the centripetal force. Okay, so that's what we have for now. We'll post the questions on the tutorial solutions a bit later. For now, that's all for now. All right.